All right, so today, let me start with this. Last time we did the parent function, so just the basic parent graphs, we didn't move them around. Now we're going to do all the transformations, and so we're going to like mess with them. This is the acronym I've always used. I don't know, you can tell me if a teacher used this before, but it's HIVO. Did a teacher ever use that with you? Or like, it's not a word. It's like PEMDAS or SOHCAHTOA. It's just a way to help you remember. The horizontal changes are inside, the vertical changes are outside. That's what that stands for. It's just a way for you to remember what's what. So if you shift something left to right, that's horizontal, that would be inside. Or if you reflect left to right, that would be inside. All the vertical changes are outside. So vertical shifts, that's where you're going to take the function and either add something or subtract something outside of it. And we're using C to stand for that. Whenever we do that, like in general notes, it's like kind of confusing because there's not an actual number there. Don't worry, when we get to an actual math problem, there will be a number and it kind of like makes more sense. Did you have a question? Okay. So what is adding something outside the function going to do to it? It goes up that amount. So it's going to be up C amount. And this is just foreshadowing to something that we're going to get to later. So I'm going to go ahead and add it in here. That means that you would add that C amount to the Y value. Because if you move up or down, you're affecting the Y coordinate of the point, like in the X comma Y scenario. So when you subtract, it's going to be the exact same thing, but everything backwards. It's going to go down that amount. And so you would subtract C from the Y value. Again, that's not really going to come into play too much today, but it's going to later this unit. So I'm just bringing it up now because this note sheet for your transformations, like everything you need is going to be like nice and neat in this one spot for you. So I'm just kind of trying to put it all there. So a horizontal shift, that means left to right. It's going to be the exact same thing that we did, except we're putting that inside of the function. And so that means it would be inside the parent function. So it would be inside the absolute value, or within the exponent if it's exponential, or within the parentheses being squared if it's quadratic. It's like inside that function. Now, these ones are kind of backwards. Do you remember that? Like the inside ones are kind of backwards. So what does this do to the function? It's going to go left that amount. And that means that you subtract C, this time from the X value. If you go left to right, that's going to affect the X part of your point. And then if inside the function you have X minus a value, that's going to move you right that amount. And so you would add whatever that is to the X value. Here's why that's the case. Give me a number, I don't care what it is. 32, is that what you said? 42, okay. Say you have X minus 42 equals 0. How would you solve that? You would add 42. So if you're trying to find like where the zeros of the functions are, like where it hits the X-axis, it's that addition that moves it to the right. That's why that's like backwards. If that helps at all, or most people just remember that it's backwards. Reflection, that involves a negative. So if we put a negative outside the function, that's going to reflect it vertically. Again, outside is vertical. So just watch me mime this. Like here's the X-axis. If you reflect vertically up and down, it's going to go over the X-axis. Is this like logically making sense? Okay. So that is going to reflect over the X-axis. So whatever was up here is now going to be down here or vice versa. And you would multiply the Y value by -1. You're oppositing, if that's a word, the Y value. Whatever's up here is now down here. But what gets people is it's over the X-axis, but it affects the Y value. Like this is the axis that you're flipping over. So I get that that's tough. If you put the negative inside means horizontal. So again, and I just like get up here and act it all out. Here's your Y-axis. Whatever's over here is now over here. You reflected horizontally. So it went over the Y-axis. And so you're going to opposite the x value. So multiply the x value by -1. What do you need me to read again? Yeah, multiply by -1. Sorry, I abbreviated multiply, M-U-L-T. My handwriting is very loopy. I'm not offended if you can't read it. Just tell me to say it again. We're usually cool up to there. The dilations is where stuff gets kind of dicey. This is where you're stretching or shrinking things, and people get hung up on that word, stretch or shrink. Just do the math part of it first, and then the word will just kind of like come secondary, right? Vertical means it's going to be outside. So if you multiply, it's going to be a coefficient. If you multiply outside the function, it's going to be vertical, and the vertical ones make sense. That would be a vertical stretch by whatever that amount is. So if you multiply to 7 outside, you're vertically stretching it to 7 times its size. And I learned that if I use this little slinky, that kind of helps. Unfortunately, it's not going to show up on the video if anyone's watching this, but I'm going to like act it out here in the classroom. So if you multiply the function by 7 on the outside, you are vertically stretching it to 7 times its size. You get what I'm saying? Like this. Right? And so you're going to multiply the y value by c. Or in, like the example I was using, by 7. You would multiply the y value by whatever that is. 7 times that. Now, if instead you have a fraction, so say it's like 1/3 out front. It's still vertical because it's still outside. Remember, outside's vertical. It's just going to this time be called a shrink. So you would shrink it to 1/3 its size. And what I tell people is don't worry about the word stretch or shrink. That's going to come naturally from how we talk. Like if I say I put this shirt in the dryer, it shrunk, it's now 1/3 of its size. That makes sense, right? If I say I put this shirt in the dryer, it shrunk, it's now twice as big. Like that doesn't make sense. So like the word stretch or shrink is just going to come like naturally. And so here you would multiply the y value by 1/c, like whatever that fraction is. So again, the outside ones make sense. The vertical ones, like vertical shifts up and down, those all make sense. It's the inside ones that are kind of backwards, which is a little bit annoying, okay? So say we multiply by a value inside of the function. So like it's inside of the absolute value or inside of the squared or whatever your function is. It's going to be horizontal because it's inside, and you have to reciprocate it. So hey guys, say that C value, it's easier if you have a number. Say it's a 4. What do you get if you reciprocate 4? And if I say something is 1/4 of the size that it was before, would I say stretch or would I say shrink? Say shrink. So think about it mathematically first, and then the word will follow. It's a horizontal shrink by that fraction. You have to reciprocate it. Again, the inside ones are the annoying ones, the ones that are kind of backwards. And so you would multiply the x value by that fraction. So it would be like this. Oh, I was forgetting to use my slinky here. So you're horizontally shrinking it. It would be like if this is your function, you take it and squish it this way. Like you're compressing it in. A lot of people call it a compression as well. I usually go stretch or shrink, but you could say it's compressed horizontally. Like it was here, and you like squeezed it inwards. And if you put a fraction inside the function, again, it's still horizontal because it's inside, but you have to reciprocate it. So like say you had a 1/9. If you reciprocate that, you would get what? 9. Like if you have that fraction, you flip it over, you just get the whole number. So if I say something is 9 times its size, I would say it's stretched. So like think about the math first, and then the word will follow. Horizontal stretch by C. And so you would multiply the x value by C. Thank you for hanging in there and getting all that down on paper, because now everything for transformations is all on one sheet for you. It's all what, like right in one place. And I like doing this example, so humor me before we get to like the actual problems, because I do think that this helps people, and it helps you tell the difference between the horizontal and vertical stretches and shrinks, okay? This too is outside. The way I know that is there aren't any parentheses with me there. Inside, you're going to see parentheses. So if it's outside, it's going to be vertical. And those ones kind of make sense. You don't have to like flip anything. So it's going to be a vertical what? Vertical stretch by 2. It's now twice as tall. We took it and stretched it this way. Okay, so let's draw a little graph. It's not going to be the Mona Lisa of graphs. It's just going to be a really quick sketch. Okay, still going to be centered at the origin. All of these are. I didn't shift them around, but I just want to plug in 1. And here's what you got to be able to do without a calculator. People always panic that the calculator gets taken away in pre-calc. This is all you have to be able to do. Can you guys multiply without a calculator and like square things? Then you're fine. All right, look, 1 squared. Very good. 1 times 2. That's basically what you need to be able to do with little numbers, okay? So you get the point 1, 2, and then the buy 1, get 1 point on the other side. And do you see how it's taller than the original parent function? Because where would that point have been if there wasn't a 2 there? Be at 1, 1. Now it's at 1, 2. We took it and stretched it this way. So let's do the one right below that. Where's the 2, outside or inside? Inside, so it's going to be horizontal. Just decide one thing at a time. These ones are kind of backwards. The horizontal shrink by 1/2. We took it and compressed the graph in this way. We took it and squeezed it. So it'll still be centered at the origin. I just want to plug in 1. Now this time we're going to do what's in the parentheses first. So, hey, boys and girls, 1 times 2. Very good. 2 squared. That's what you got to be able to do without a calculator. That's it. So if you were like panicking about that, that's all you have to be able to do. So we get the point 1, 4, bonus point on the other side. And I want us to do a compare and contrast between those 2 graphs. Both of them got taller, or I guess I should say narrower. They both became narrower. So in both of these cases, it was more narrow. But which one is more narrow, the outside or the inside one? Like which one had more effects? The inside one made it more narrow. Are you guys seeing that? That's the takeaway. Now we're going to do the same thing with the 1/2. Where is this 1/2, outside or inside? Outside, so it's going to be vertical. Shrink, those are the ones that make sense. The outside ones are kind of like logical. Vertical shrink by 1/2. This is the one where it's like an elephant came by and sat on it. Like you came by and just like squished it this way. So let's try and plug in a number. I'm going to plug in 2 in this case because there's a fraction. I just don't want to have to deal with the fraction. All right, 2 squared is 4. Good job. 1/2 of 4 is 2. So we get the point 2, 2, and same thing on the other side. So the way I know that that's been squashed a little bit is in the parent function, the point would have been 2, 4. Now it's 2, 2, like an elephant came by and sat on it. And then this last one, where's the 1/2? So it's horizontal. Just decide that first and then take a breath because you don't have to do everything all at once. Do one thing at a time. Horizontal and then go, oh, it's horizontal. That means it's going to be kind of backwards. Stretch, good. By 2, you have to reciprocate it. So again, I just want to plug in 2. We don't need like a ton of points here. I just want you to compare. So if you plug in 2, this time you have to do what's in the parentheses first. So hey guys, what's 1/2 of 2? 1, and then 1 squared is 1. So you get the point 2, 1. So again, you've just got to be able to plug in numbers. Like if you can add, subtract, multiply, divide little numbers, like single digit numbers, and like square and cube some small numbers, that's really all you need to be able to do without a calculator in here. It's not anymore. Oh wait, I was going to say one more thing about that. Both of these made the graph wider. So these ones make it narrow. If there's a fraction, it becomes wider. Which one is more wider? I know that's not good English, but like which one had more of effect, the outside or the inside? But we're shrinking this time. So which one is like more wide? Yeah, this one's going to be more wide. So the takeaway is Do the outsides or the insides have more effect on the graph? Why would that be the case? Why would inside the function have more oomph? You're affecting the variable before the function happens. So you're affecting the variable before you square or before you cube or before you do any of the rest. Okay. Thanks for humoring me. I like to explain that. We're just going to do a few examples. Here's where I like to highlight. If you don't want to do that, if you're like, oh, this won't help me, then don't, okay? But what I have people do is highlight the inside, and then whatever's not highlighted will be the outside. Does that make sense? Go ahead and put the phone away. So if you highlight the inside, whatever's not highlighted is outside, and it helps you tell the difference. So first, let's say the parent function. What is this parent function? Rational, good. So we should already be thinking like, hey, go ahead and put the phone on. Where, like, what does it look like? You know, like already be thinking about that. And then if you want to highlight, and again, you don't have to, I'm just throwing it out there. That's the insides. What's the root word of rational again? Ratio. It means fraction, something over something else. So the fraction is the function. What'd you say? Rad? Yeah, no. That is funny though. So let's start with the outside. The negative didn't get highlighted. So the negative is outside. Flip back if you have to. If the negative's outside, which axis did you reflect over? X. Good. It's a vertical reflection. And then the x plus 3 is inside. That means left or right, and it's kind of backward. Not kind of, it is backwards. So we went left 3. Now, I'm not super picky about plotting points for rational because those graphs are kind of crazy. As long as the asymptotes are in the right place, we're good. So we want to shift left 3. And normally the asymptotes are on the axes, but you're just going to shift left 3. It didn't go up or down, so the other asymptote's still on the axis. And then like normally, or I guess I'm not writing that. Normally the graph would be like this. Don't write that though. Why is it not going to be in like these two quadrants, so to speak? We reflect it upside down, so it's going to be in these two. And again, I don't need real like picky points for that because those graphs are just so weird. As long as you have it like in the right place and it doesn't go across the asymptotes, then you're good. So it's just upside down. Look, you graphed without a calculator. See, you don't need it. You're all brilliant. All right, my suggestion is let's highlight what's inside the function. Then anything that's not highlighted, you know that's outside. Just helps you keep it separate. And I'm going to give you the correct number. This always cracks me up. I'm going to give you the correct number of lines for the answer. I always have somebody that adds like an extra line or like scratches out a line. Like, don't do that. I'm trying to help you out, right? What is this parent function? All right, absolute value. And we are going to talk about the order of the transformations later this unit, but for right now, I don't care what order you put them in. So somebody just shout them out. What is one thing that like happened to this graph? Reflect over y, that's the negative that's inside. So reflect y-axis. Vertical shrink, that's the 1/2. So vertical shrink by 1/2. Give everyone a chance to write it down. This is like an elephant came by and sat on it. It got squashed to half its size. Left 2, good. It is horizontal, but you don't have to say like horizontal left 2. You know, I do get people that do that, and that's totally fine, but yeah, like verbally. I know, and I love when you guys talk to me. Just don't worry. I'm not going to yank you in the hallway and make you take a verbal exam like you do in your language class. I realize that the math stuff is hard to say a lot of the time. So as long as you're awake and talking to me. And then down 3, perfect. So the shape for absolute values of V, we just need to do these things to it. So the center of the V, instead of being at the origin, just go left 2 and down 3. And now that's where the center is. Now it also got reflected over Y. Let's talk about that real quick though. Here's your absolute value graph. If I reflect over Y, what happened? Like it happened, but it didn't, if that makes sense. So like you kind of don't need to worry about that one. Now, if it reflected over X, it would be upside down, okay? But we kind of don't need to worry about that one, which is really nice, okay? And whenever it's absolute value, both sides are linear. So you can just use this 1/2 as your slope. So from this center point, you can go up 1 over 2 and just use it as your slope because it's a line, you know, like let the slope instinct kind of kick in there. And you guys are awesome. You're staying awake and talking to me, so we will definitely be able to finish a little bit earlier. I always like to finish early. That's my goal, to give you like the last few minutes to like, I don't know, recenter your mind before you got to go somewhere else. All right, if you want to highlight for this one, you don't have to. Again, I'm just throwing it out there. Like it does sometimes help people. It helps you see what's inside and what's outside. So what is this parent function? It is exponential. I'll take abbreviations on a quiz or test. Okay, I'm going to write out the whole thing just to be thorough. But I will take an abbreviation on a quiz or test. I'm a very poor speller, so I will never like grade your spelling. Like as a math brain person, spelling is like not my thing. All right, two transformations. Again, right now I don't care what order they're in. So what's one thing that happened? Down 4. Good. You guys are good on those reflections. Oops. The reflections are usually hard for people because one, I get it, one's one way and one's the other. So exponential is a swoop, okay, with that horizontal asymptote. We moved down 4 though, so instead of the asymptote being right in the middle, go down 4. Now the 3 is just the base, it's kind of just there. For this one, to get some points, like here, I didn't need any picky points. And here we just kind of used the slope. For this one, I would probably just go ahead and make a table. I usually like to see at least 3 points or something like that. What is the easiest point to plug in? Like if you have to start and you just don't know where it's the easiest number to plug in. 0 or 1, right? So let's start with 0, okay? You can't negative a 0. What's 3 to the 0? Think about it first. Good, 1, whoever said that back there, thank you. Anything to the 0 power is 1, and then 1 minus 4 is -3. Perfect, 0, -3. Now I need another number to plug in. 1. Now, if we try 1, we get 3 to the -1. Yeah, yikes, right? If that's your reaction, that means you're a normal person, okay? If that happens, pick something else. Instead of 1, what can we maybe do? Good, because if you plug in -1, what's going to happen? Make it +1. What's 3 to the 1? 3 minus 4 is -1. If you try to plug in a number that doesn't work out, pick something else. It's like no biggie. I tell my son all the time, it's try again. Try again. And then let's do -2. If you plug in -2, negatives cancel. 3 to the 2, 3 squared. No. Good, don't say that. 9 minus 4 is 5, -2, 5. Why is the swoop going down instead of up? Why is it decreasing instead of increasing? Because we did what? It was because of the reflection. Good. All right, this one has those like double bars. Do you remember what that is? Greatest integer. And yes, it will look like a staircase. So there's nothing going on inside the function. All I highlighted there was the x. So both these things are outside. What's one thing that's happened? Vertical what? Stretch, good, by 3. So we made it 3 times as tall. Took it and stretched it this way. And then up 1. Thank you. So normally you start at the origin. We're just gonna go up 1. So you're gonna go up 1 and put a point. Here, and I'll zoom way in for this one. And that's where your first step is, okay? That first like little barbell. You're gonna go up 3 for the next step. We stretched it vertically by 3. The step graphs are great for you to see those stretches and shrinks. This is a staircase that would give you a really big workout because the steps are 3 units apart from each other. So you stretched it vertically. And I think I put the next one a step graph as well, except I did it horizontal. Yeah, because The step graphs help you see that very, very visually. So I like them for that. Because yeah, I made this one a horizontal. So this is the same thing. You can write greatest integer again if you want to or not. It's the same thing. But what are the transformations for this one? Good. It's a stretch because you have to flip it. So horizontal stretch by 2. And then down 3. So here's visually what happened. We stretched it this way, like an accordion. I love having this little slinky up here. Plus, I also need a fidget. So we took it and stretched it this way. So the stairs are still just going to be 1 unit apart, but they're going to be like deeper stairs. I find those staircases annoying. Do you ever like walk up steps where it's like such a deep step that you almost have to like take a step in between like each one? Yeah, that's what this is going to look like. So we'll start by going down 3. And I'll zoom way in on this one again so you can see it. So we started by going down 3, but the stairs themselves are going to be twice as wide. So the stair itself is 2 units in length, but they're still only 1 unit apart. Like we didn't do anything vertically. It just got stretched horizontally. And again, those step graphs are great for seeing that visually, like the stretches. To tell the difference between vertical and horizontal, you can just see it really well with that. Okay, we're not gonna have to graph anything else. The rest of these, you're just gonna write the answers. Yes, sir. Oh yeah, I just wanna see at least 3 steps. It goes on forever in both directions. It's an infinite staircase. Oh, whoops, except I went a little farther. It's only 2 units. I know, right? Boggles the imagination. Okay, for these, it just says write the equation with those given transformations. So you need to put an f of x equals or a y equals for an equation. So this one's going to be cube root. So you can draw like a blank cube root, and then we're going to do these things to it. So we want a horizontal shrink by 1/4. First question, if it's horizontal, where does it go? Inside, perfect. Those ones are kind of backwards. So it's not going to be a 1/4, it's going to be a 4. So inside, you're going to put a 4. You're like building it, so to speak. But don't try to do it all at once. That's overwhelming. One thing at a time. Right 2, left and right, where does that go? Give me inside, and good. It'll be -2 because it's kind of backwards. Now here's the thing that people miss. You have to put parentheses around it. I always say, give it a hug. Just give it a hug. You can't give too many hugs. Just put parentheses everywhere if you're not sure, okay? Hugs. That's it. That's all we had to do for that. All right, this one, f of x equals, write the word log. I just draw it blank, and then we're going to like fill it in. That kind of calms you down because you're like, all right, I got the framework. Now I just have to fill it in. Reflected over y. Okay, it's like I know there's a negative, but where does it go? Just calm down. It's going to be where? Inside, good. Because if this is the y-axis, you reflected horizontally, left to right. All right, vertical, that's going to be outside, shrink by 1/3. Those ones just make sense. You're just going to stick a 1/3 out front. And then up 8. So that's going to go, it'll just be tacked on at the end. Okay, there's one thing I didn't put, and I kind of left too much room because I wasn't sure how much space I would need. What else has to go in there with the negative? Yeah, like you have to have a variable. All right, what is this one called? The name. Square root. And we're going to say what happened to it. And then like we just did, we'll build the equation. Good. It reflected over y. Okay, hold on. Let me write it. I love that you guys are excited to say the answer, but I got to give everyone a chance to write it. Reflect over y-axis. And then instead of being centered at the origin, it went right 3. That's where that like starting point is. So when you do your equation, just write f of x equals and just draw a blank square root. Just leave it blank. That's like your skeleton of the thing. And then you can just go back and fill it in. Oh, I know a reflection is a negative. Where does it go? This one's inside. The more practice you get, the better it'll go. And we have to do x minus 3. Where does it go? And you have to give it a hug. Okay, so x minus 3 goes inside. Also with the square roots, if you guys could all just do me a big favor, make sure that it's long enough to cover what you want. Because here's where I run into an issue is if people write this on their paper, grading it becomes difficult for me because I'm like, well, did they know or like that was supposed to be, do you get what I'm saying? So like, just help me out and like make sure it goes far enough so that I can just go ahead and give you credit. Because then I sit there pondering forever, like, what did they mean? All right, last one. What is this one called? I know it's like it's either cubic or cube root, one or the, I know it's like one is one way and one's the other. It is cubic. The way you can tell, did we talk about that last time? I can't remember. The roots, like roots of a tree, they grow out sideways, if that helps at all. All right, so that where's the center? So we went down 1, perfect. Left 2. Oh, now let's have a conversation about that. Did we reflect over y or did we reflect over x, or does it actually not matter? It actually doesn't matter which way you went for this one because the graph is symmetric every which way. If you have a choice, pick x. Okay, it is easier to put a negative outside than inside. Does that make sense? Like if you have a choice, go the easy route. All right, so reflect x-axis. So I don't know who said that back there, who said y. You are totally correct. Full credit on a quiz or test. It's just it's easier to write the equation if you do x because you can put the negative just out front. So I'm just looking out for you. I just want you to do it the easier way. All right, so I've got the negative. What do I need to like do next? I need something cubed because it's cubic. So something to the third if you want to like leave a blank cube. Good, x plus 2, that's for the left 2, and then minus 1. The back is not homework. Your homework's on Delta Math, but I like these because they're self-checking. If you want to do this for practice, if you get it to say something, then you know you did it right. Does that make sense? Like you don't need the answers from me to know that you did it correct. So that's just there for extra practice if you would like it. Your homework is on Delta Math. Alrighty?